Welcome to another data science deep dive on a technical track. The following presentation is by Sifeng Lin, research scientist at DoorDash. Common methodologies used to optimize conventional logistics systems are less applicable to improving the efficiency of DoorDash's real-time last-mile logistics platform. These common methodologies require a stable prototype environment that is difficult to build, and their platform does not allow for the accurate measurement of the algorithm change. To address this specific use case, Sifeng and his team designed an experiment-based framework that allows them to rapidly iterate their algorithms and accurately measure the impact of every algorithm change. Enjoy the presentation.
Hello, everyone. My name is Sifeng Lin, an operations research scientist at DoorDash. I'm really glad to share with you our practice of solving the real-time assignment optimization problem. Specifically, we use an experiment-based framework to optimize the real-time food delivery assignment. Here is what I'm going to go over with you today. So first, I will briefly introduce the real-time assignment problem in food delivery. And then I will share our model, which is a mixed integer programming formulation. After that, I will share our practice of iterating the experiment through experimentation. And finally, the question and answer. Here in these slides, I share a few logistic systems in the conventional way. If we define the lead time as the initiation of the delivery to the time the service is delivered, we can see that the lead time can range from years, or if you are planning for moon landing, to 1 day or two if you are doing the Amazon delivery. The sea shipping, it's probably the slowest on earth. It can take months to plan for and get your things delivered. I used to work in the railway industry, so I know that the railways, they have a different level of lead times. It can range from months for the delivery of the coal on the ground to a few days for the UPS fast trains. And nowadays, during the pandemic, people use online shopping a lot. Amazon has been the benchmark in performing all those fast deliveries. In the places I live, Bay Area, you can actually get things delivered within a day for some popular items. Some other retailers like Best Buy, they are definitely catching up. And in the smartphone, we do enter a new age where the lead time of delivery is cut from days to hours, minutes, or even seconds. There are three representative examples here. First of all, it's Instacart. They offer grocery delivery. If you place an order, normally you get it within a few hours. The second example is in the DoorDash, the company I work for. We started as a food delivery business, and once you place an order, you expect that you get your delivery within an hour or so. Uber is even more real time or more responsive. Once you request a ride, I believe you also expect it to come within a few minutes. Otherwise, you may just switch to Lyft. So these examples, they represent the modern real-time logistics system that people really want your delivery to get to you fast. And the second characteristic is that these businesses are actually platforms, which means that they don't own the inventory of all those logistic systems, like they don't own the vehicles. And employees working in these platforms are actually gig workers, independent contractors, instead of the regular employee. And I'm going to show that these two characteristics is going to make the logistic optimization problem very different from the traditional one. Before we get into the problem context, let me briefly introduce DoorDash. DoorDash is a technology company that launches the logistic platform to facilitate the last mile deliveries. We seek to connect consumers, merchants, and drivers in the most efficient manner possible. There are three players in this marketplace. First of all, it's the consumers. They want their food delivered, they want their grocery delivered, and they want their flowers delivered. And there are merchants who offer all those services or commodities that the consumer wants. And also we have dashers who picks up all those commodities from the merchants and then do the delivery to the customer. And DoorDash's marketplace seeks to connect all those three elements together. Now let's look at the life cycle of delivery order in DoorDash's system. At the very beginning, the consumer initiated an order, then through DoorDash's platform. After DoorDash gets this order, two things happen simultaneously. First of all, we need to send the delivery to the merchant, and the merchant starts preparing for the food, making sure that the consumer is happy about their commodity. And the second thing is DoorDash needs to decide which orders should be sent to which dashers, so that the dasher can pick up an order from the merchant and then do the delivery to the consumer. This whole process, for the majority of the deliveries in our system, it takes no more than 1 hour. Today, we are going to focus on the part that how we decide which dasher should take which delivery. The problem we are trying to solve is we need to assign the right deliveries to the right dashers in order to maximize both the delivery quality and also the delivery efficiency. Yeah, again, the goal is to assign the right deliveries to the right dashers. And what kind of problem context are we in? As I mentioned, all the information in this system is real time. Deliveries comes in continuously throughout the day, and then once they are placed, we normally try to get it to the customer within an hour or so. And the dashers check-in and the check-out throughout of the day. Those information are highly volatile. Given that we have really stringent service requirements, so normally we make our decisions in real time, meaning once an order comes in, we normally make the decision within a few minutes. Another challenging factor is that dashers are independent contractors, which means if you give them a task or an assignment, they may accept it and they may decline it. It's all by their choice. Theoretically, you can model the whole problem as a Markov decision process optimization, set up state space, doing some calculating some transition probability, designing some heuristic. But that's not how it works in industry. In industry, as far as I know, most companies first convert this real-time problem into a static optimization problem by taking a snapshot of the real world every once in a while. Once you have a snapshot, then you have an optimization problem that you can solve. You can optimize the assignment of deliveries to dashers in this snapshot. The technique we use to optimize this snapshot is called the mixed integer programming model. It's a technique to solve the optimization problem. In short form, it seeks to minimize or maximize an objective function subject to a set of constraints. Once you have this model, you can use some commercial solvers or open source solvers to solve the problem. And now let me quickly go over our mixed integer programming model for you. First, define a few notations. We use D to represent the delivery, R to represent the route, S to represent the dasher. And here we have the cost of CRS, which means the score of offering the route R to dasher S. This is a score that combines the route and also the delivery speed and also the delivery efficiency. Let me now quickly go over our mixed integer programming model for you. First, we define the notation. D is for delivery, R is for a route, and S is for a dasher. Here, the CRS, the score of offering the route R to the dasher S, it's going to be a score that combines the delivery speed and also the delivery efficiency. Most companies probably have their secret sauce of defining the CRS to make sure that the model can represent their business priorities. So here the XRS is our decision variable. It represents 1 if we offer the route R to the dasher S, and 0 otherwise. Our objective is to maximize the total score of all the decisions. So we sum up all the assignment of the route R to the S and their score, maximize it. There are a few constraints in this system. First of all, it's that every delivery can be offered at most once. And the second one is that a dasher can be matched to at most one route, which means that you cannot assign one dasher to perform multiple jobs. There may be other business constraints in the system that we need to follow. Once we have the model ready, then we need to put it into production. And how do we decide if this model actually performs better than the existing one? That's a very hard problem. It's especially hard in our real-time context. So the gold standard to deciding which one is better is always experiment in industry. If we are going to run the experiment, what would we actually randomize it on? Obviously, we cannot randomize on the delivery level because optimization problem is trying to coordinate across deliveries, multiple deliveries. So there are network effect between those deliveries. The next choice is probably, and maybe the most scientific one, is to do the region level randomization. But then the power is very, very low. DoorDash currently operate in around 4,000 cities, which means you only get 4,000 units of data. That's far away from getting enough power to detect anything. And another thing is it's really hard to capture the difference between cities. So what we ended up is using a switchback experiment framework, which means that our randomization unit is the region time window. The time window could be 1 hour, 2 hours, or 4 hours, depending on your situation. What we do is at any region, at any given time window, we randomly pick an algorithm, and then this algorithm is going to be run at this region at this window of time. So let's look at the example of switchback experiment. So suppose that you pick a window size of 30 minutes, and you have a region A, region B, and all those regions. And this chart basically shows that we run control here during 10:30 and 11, shipment here between 12:30 and 1 p.m. So once we do this, and then the algorithm iteration, it basically turns into a normal A/B test. And the experiment result is going to tell us what our matrix looks like for each of these control treatment algorithm. One thing that we learned hard is that once you are running the switchback experiment, you really need to worry about the clustering when you are calculating your p-value. Since we done the switchback experiment framework, we have decided to move most of to test most of our ideas in switchback. Why do we decide this, and why is this experiment so important to us? The main reason is that the offline algorithm iteration is almost impossible in our real-time volatile context. First of all, the business logic is changing very, very fast. And the information in our context is highly volatile, so it's hard really to capture offline data for accurate modeling. We may try to build a simulation environment, but then that's going to be too hard, and involve way too much effort. So currently we are running a lot of experiment in the platform. What kind of thing do we experiment? We experiment on all spectrum of the model. First of all, is the input data preparation. How do we actually capture the snapshot of input data, better prepare it for the optimization? We also experiment on all aspects of the mixed integer programming model, including its objective function, the constraint definition, and also how we process the output from the mixed integer programming model and send them to execution by Dash. If you think about the switchback experiment, every time we are trying to shape the experiment that improves the overall system metrics. This means that we are trying to find a better algorithm experiment by searching for the local optimal. And over time, we do see that our metrics and also algorithm improves over time. As I mentioned, now we run 100 experiments per month, just simultaneous to test to see if we can improve our assignment algorithm. This is a huge improvement over what I have already have done, and it's coming from all those optimization we have done in multiple dimensions, including the culture, process, expertise, and platform. First of all, internally inside the team, we really develop a culture of get down to the lowest level of details to look for all possible insights that can improve the assignment algorithm. And once we have the insight, we always encourage people to run experiment, to fail fast and also learn fast. The second thing is critical to us is we have a well-defined experimentation process. First of all, we standardize the metrics and also the experiment stripping criteria. So every experiment owner knows what they expect once they are running the experiment. We also design our experimentation system so that it can handle as many experiments as we want, while still measure our results accurately. This requires really close collaboration between the engineering team, product team, analytics team, and also the platform team. Over the time, we also work really hard to develop deep expertise into the switchback experimentation framework. The help from the academicians is really critical here. Stanford's Professor Sunny from Stanford University really helped us develop all those methodologies on window size, network effect, variance reduction, and also the interactions between experiments. Also, the support from our tech and the platformization team is critical. They really help us develop, customize the technology and also the analytics in order to make sure our experiments are run and also analyzed in a really fast fashion. So in short, we have the culture, process, expertise, and platformization ready to help scale up as our experiment, making sure that we are always improving the algorithm through experimentation. So that's all I want to share today. So I just introduced the real-time last mile logistic problem and showing that why it's hard and important. And also I'm sharing our mixed integer programming formulation for solving the assignment problem. And finally, I shared how our experiment-based framework really help us iterate and evolve our assignment algorithms. Thank you for your attention, and I'm happy to take any questions.
That was Sifeng Lin, research scientist at DoorDash. Sifeng shared a specific use case where his team designed an experimental-based framework that allowed them to rapidly iterate their algorithms and accurately measure the impact of every algorithm change. If you like to watch more videos like this, make sure to subscribe to the DSS Insider program, where you can see our complete on-demand video library, and watch it whenever you like on your own time. And also make sure to subscribe to our channel below. Thanks!